Hello friends, welcome to AP Calculus course for BC test. Now we will consider the topic continuity, okay, as per BC syllabus. Okay, these are the two chapters to be covered under continuity: continuity definition and introduction, and types of discontinuities. So for that you have to have a clear understanding of functions and limits to understand continuity, and these are the reference books for this particular topic, that is continuity. Now let us see what do we understand by continuity. What do you understand when you say function is continuous? Say y equal to fx is a function, real function. Of single variable x. X is the independent variable and y is the dependent variable, and for all real values of x, y is also real. Now, what do you understand when you say a function is continuous? If the graph of a function can be traced with a pencil without lifting the pencil from the page, the function is continuous. That means if you plot the function on graph paper, on a piece of paper, and if you need not lift the pen from the paper, then while drawing the function, then the function is continuous. But if it is such that the function is like this, then see, you are drawing like this, then you have to lift the pen from plane of the paper or page, and then you draw the remaining part of the function. So here the function is discontinuous. It is discontinuous. Whereas this is a continuous function. Okay. So if the graph of a function can be traced with a pencil without lifting the pencil from the page, the function is continuous. This is the basic understanding by which we mean whether a function is continuous or not. If the graph of the function does not have any break or hole in it within certain interval, the function is continuous over that interval. So in this given interval, say this to this, x equal to a to x equal to b, there is no break or hole in the function. But here you see there is a break in the function in the interval x equal to a to x equal to b. So function is discontinuous. Now we have come across a new term, hole. Break means function, there is a break. Hole means what? Let us try to understand. A hole is a point on the graph where the value of the function is not defined. It may so happen that the value of the function is not defined at some point. Okay, so function is like this, fx and x, and it is such that at this point the value of the function is not defined. At this point, say x equal to, this is x equal to a point. At this point the value of the function is not defined at all. Okay. So we represent this by a small circle, hollow circle. So it is a hole. If, say for example, say fx is a function like this, x into x minus 1 by x minus 1, or you can write x square minus x by x minus 1. So you see, at x equal to 1, the value of the function is undefined, because in that case x equal to 1, function value becomes 0 by 0, indeterminate form. So x equal to 1, a normal a function like this, it is undefined at x equal to 1. So we say the function has a hole in it at x equal to 1. Okay. Or a function like this where the value of the function is not defined at x equal to a. Okay. So if the graph of the function does not have any break or hole in it within certain interval, the function is continuous over that interval. Okay. And hole is what? At that point, at a particular point, if the function is not defined, then it is generally said that the function has a hole over there. If the numerator and denominator of a rational function have a common factor like this, both numerator and denominator have a common factor x minus 1, they will cancel when simplifying, and this cancelled value creates a hole in the graph. So it is cancelled for all x other than, it can be cancelled when x is not equal to 1. And it is at x equal to 1, this cancellation does not work because the function is not defined. The fx equal to x into x minus 1 divided by x minus 1, fx can be written equal to x provided x is not equal to 1, because at x equal to 1, both numerator and denominator become 0. Okay. Say this example already you have drawn, that this is a separate, not exactly the previous one. Here the function is y equal to x square minus 1 by x minus 1. So it is x plus 1 into x minus 1 divided by x minus 1. So when x is not equal to 1, y is x plus 1. So y is x plus 1 means it is a straight line. This is y, this is x, and this is y equal to x plus 1 has intercept. This is 0, 1 point, and this is negative 1, 0 point. Negative 1, 0, and this is 0, 1. Okay, and this is the straight line, but at x equal to 1, so when x is not equal to 1, y is x 1 plus x, like this straight line. But this is the original equation, original function, but at x equal to 1, y is actually in 0 by 0 form. So at x equal to 1, this is x equal to 1, the value of the function is not defined at all, because at x equal to 1, function has a hole in it. Okay, because value of the function cannot be determined. Y is indeterminate at x equal to 1. So function has a hole in it. So if the function is like this, function can always be written as y equal to x plus 1, provided x is not equal to 1. And at x equal to 1, the value of the function is indeterminate. Okay, so the function is said to be discontinuous at x equal to 1, and it has a hole at x equal to 1. Okay, had the function been defined like this, x plus 1, then the value of the function at x equal to 1 would have become y equal to 2. But since the function is defined like this at x equal to 1, the value of the function is in indeterminate form. So the true graphical representation of the function will be like this. Okay, other than x equal to 1, the plot will look like y equal to x plus 1 straight line. But at x equal to 1, the value of the function cannot be determined, and this thing is represented by drawing a hole at this point. Okay. Now, how we can determine? So, this was the qualitative definition of, you can say, continuity. But how you can test whether a function fx is continuous at x equal to a. How to check? How to test rather? Testing of continuity. So, a function fx is said to be continuous at x equal to a if fa exists and define limit x tends to a positive fx exists and defined. That means this is the right hand limit. Left hand limit, that means limit x tends to a fx exists and defined, and if they are equal means that means the limit of the function x tends to a fx exists. Then, and if this fa is equal to this thing, then we say the function is continuous at x equal to a. So ultimately, this is the testing criteria. If value of the function at x equal to a is equal to left hand limit of the function as x approaches a is equal to right hand limit of the function as x approaches a, and if they are equal, then limit exists, and this is limiting value, limit x tends to fx. So if fa is equal to limit x tends to a fx, and limit x tends to fx exists only when this thing limit x tends to a plus fx is equal to limit x tends to a minus fx. So if limit of the function exists and if it is equal to the value of the function at x equal to a, then we say the function fx is continuous at x equal to a. So this is the criteria to check whether a function is continuous at x equal to a or not. Okay. So consider a problem. Check the continuity of the function fx at x equal to 0, where fx is defined as fx equal to x plus 1 for x less than 2, and fx is 2x minus 1 for x greater than equal to 2. Both are linear functions that both represent straight line but with different slopes, you can say. So f2, we have to test the continuity of the function at x equal to 2. So that means we have to check whether x2 plus fx limit x tends to 2 negative fx, and if we have to test, find the value of f2. If these three are equal, then we can say that the function is continuous at x equal to 2. If they are not equal, then function is not continuous at x equal to 2. So f2, while evaluating f2, we have to use this formula because fx is 2x minus 1 for x greater than equal to 2. So f2 is 2 into 2 minus 1 equal to 3. So f2 is 3. Left hand limit, this is the left hand limit, LHL, this is the LHL. So limit x tends to negative side, from negative side fx. So when x is less than 2, so it is becoming fx is x plus 1, so 2 plus 1. So limit x tends to 2 from negative side fx is actually limit x tends to 2, fx is x plus 1. So it is 3. Okay. And so this is the LHL. And RHL is limit x tends to 2 from positive side fx. When x is more than 2, so your function is 2x minus 1. So again it is 3. 2 into 2 minus 1 is 3. So LHL is equal to RHL, and value of the function is f2 is obviously 2 into 2 minus 1 is 3. So LHL equal to RHL equal to f2. Therefore, fx is continuous at x equal to 2. You can draw the graph of this function for x less than 2 and x greater than equal to 2, and you will really find that the function is actually continuous. You can test it yourself. Then another problem, check the continuity of fx at x equal to 2, where fx is defined as fx equal to x plus 1 for x less than 2, like previous one. Fx is 2x minus 1 for x greater than 2, but fx is equal to x square at x equal to 2. Functions definition for 3 different regions are different. At x equal to 2, fx is x square, and for x greater than 2, value of fx is determined using this functional form, and when x is less than 2, value of fx is determined using this formula. So f2 is actually 2 square is 4, and LHL when x is less than 2, it is actually 2 plus 1, 3, and when RHL we are calculating, it is x is greater than 2, so it is 2 into 2 minus 1, again it is 3. So though limit exists, but the limit exists, limit extends to 2, fx exists, and its value is 3, but limit extends to 2, fx is not equal to f2, because f2 is 4. Therefore, the function is not continuous at x equal to 2. Okay. Another problem, check the continuity of the function fx equal to mod x by x. Mod x by x. So fx is mod x by x. Mod x definition we know, mod x is actually x for x greater than 0, and mod x is negative of x for x less than 0. So mod x by x, so if I plot fx versus x, so fx when x is greater than 0, mod x is x by x, it is 1. So it is 1. And fx when x is less than 0, mod x is actually negative of x divided by x, it is negative of 1. So it is like this. So function apparently, and value of the function is undefined, indeterminate at x equal to 0. So function is discontinuous clearly at x equal to 0. So we can, if you calculate the limit x tends to 0 positive fx, when x is approaching 0 from positive side, we can always write x is 0 plus delta, but delta is a positive quantity. So you can write x tends to 0 plus fx is mod x by x. Mod x is, and as x approaches 0, delta is approaching 0, so I can write it is delta tends to 0, x is mod delta divided by delta, so it is unity. So left hand limit, right hand limit RHL, this thing limit x tends to 0 fx is plus 1, that is like this. Now when if we calculate this thing, so it is this thing, and here when x is approaching 0 from negative side, I can write x as 0 minus delta. Okay, so x we can write in place of x, I can write minus delta, negative of delta, and here I can write negative of delta mod. Okay, let me write it once again. X is negative of delta divided, and on the top numerator it is negative of delta. So it is basically limit delta tends to 0, delta divided by negative of delta. So it is negative of 1. So right hand limit, left hand limit is negative of 1. So limit does not exist. Since the limit does not exist and value of the function is also indeterminate and limit does not exist, this is sufficient to say that fx is not continuous at x equal to 0. Okay, so once again I am telling you, we have to test whether limit x tends to a fx, limit, you have to check this value, and fa. You have to compute separately these three quantities, and if they are equal, then only the function is said to be continuous at x equal to a. Okay. Now, what are the different types of discontinuities? There are basically three types of discontinuities of a function. One is called jump discontinuity, another is called essential discontinuity, another is called removable discontinuity. Let us see what are these three types of discontinuities. So, jump discontinuity is what? Jump discontinuity is something like this. A jump discontinuity, at jump discontinuity, the curve breaks at a particular place and starts somewhere else. Both the left hand limit and right hand limit exist at that point, but they do not match. So, function is like this. Function as x increases, it is moving like this. Then at x equal to -1, again it jumps to some other value and moves like this. So the value of, if you consider the limit of the function at, this is x equal to -1, okay. So as x approaches -1 from negative side of -1, that means limit x tends to -1 from negative side fx, this is this much, and this is actually +1 as per the figure, okay. And as limit x tends to 1 from -1 from positive side fx, if you calculate, this value is actually 2. And these two limits are not equal. LHL is not equal to RHL. So function is discontinuous, and the limiting values are finite limiting values. This is a finite number, this is a finite number, but they are finite. They do exist, but they are not equal. Okay, so it is a jump discontinuity. That means at particular point x equal to -1, the value of the function jumps from 1 to 2. So this is an example of jump discontinuity. If limit x tends to a plus fx and limit x tends to a minus fx both exist and different and neither take on values plus minus infinity, and these values are finite values, limiting values, they are not infinity, then we have a germ discontinuity at x equal to a. This is important, and neither take on values plus minus infinity. In the figure there is a germ discontinuity at x equal to -1. That means if the nature of the function is such that for a particular point x equal to a, limit x tends to a from positive side fx, it is something L1. L1 is not plus infinity, L1 is not equal to plus minus infinity. L1 is a finite number, and limit x tends to a from negative side fx, it exists and its value is L2, and L2 is also not equal to plus minus infinity. Okay. Then, and L1 is also not equal to L2. So L1, L2, they are neither equal to plus infinity nor equal to minus infinity, and they are not equal to each other. Then we say the function is having a germ discontinuity at x equal to a. Okay, and the character is like this. The function is going like this. This is a germ discontinuity at x equal to a. The value of the function jumps from this value to this value. So it is a germ discontinuity, and jumps from one finite value to another finite value at certain point x equal to a. So if the character of the function is such that at a particular point the value of the function jumps from one finite value to another finite value, then we say the function has a germ discontinuity at that point. Okay. Essential discontinuity. What is essential discontinuity? A function fx has an essential or infinite discontinuity. It is also called infinite discontinuity at x equal to a if limit x tends to a negative side fx is either plus infinity or minus infinity, or x tends to a plus limit fx is plus minus infinity, either of this. That means function limit x tends to a from positive side fx is either plus infinity or negative infinity, and limit x tends to a, I can write in a better way like this. Or limit x tends to a negative side fx is plus infinity, plus minus infinity. That means either plus infinity or minus infinity. That means if the left hand limit, magnitude of the left hand limit is infinity, maybe positive infinity or negative infinity, or the right hand limit is positive infinity or negative infinity, then we say that the function has a essential discontinuity. Remember, left hand limit is positive infinity or negative infinity, or right hand limit is positive infinity or negative infinity. It may so happen that both are infinity. So many cases may arise. That means only limit x tends to a plus fx is plus infinity, or limit x tends to a plus fx is negative infinity, or limit x tends to a negative side fx is plus infinity, or limit x tends to a negative side fx is negative infinity. If out of these four criteria, if anything happens, then we say the function has a infinite discontinuity at x equal to a. Say it may so happen that this condition is satisfied and this condition is satisfied. That means left hand limit is plus infinity, right hand limit is plus infinity. It may also happen. Left hand limit is plus infinity, right hand limit is negative infinity. It may come like, the situation may come like this. Only left hand limit is infinity, but right hand limit is not infinity. It is a finite number. Then also it is an essential discontinuity. That means the left hand limit is either like this or like this. This is x equal to a. Left hand limit is either plus infinity or negative infinity, or right hand limit is positive infinity or negative infinity. Then we say the function has an essential discontinuity. We will see some situations actually. Here you see, in this example, as x is approaching a, this is x and this is fx. Here, as x approaches a from negative side fx, it is as x approaches a, fx approaches positive infinity. Limit x tends to a from positive side fx, it is also positive infinity. So it has the essential discontinuity at x equal to a. Here both LHL and RHL are positive infinity. This is one situation. Okay. Here you see another situation. This particular point is x equal to negative of 1. Function is like this, and there is a jump. Here it is finite value, it is 1 plus 1, and it jumps from plus 1 value to negative infinity. Okay, so limit x tends to 1 from negative side fx is plus 1, whereas limit x tends to 1 from positive side when x is approaching to negative of 1, sorry, it is negative of 1, this is negative of 1. Again I will draw. This is negative of 1 point, x equal to negative of 1. So when limit x tends to negative of 1 from negative side fx, x is approaching negative of 1 from negative side of negative 1, it is reaching a finite value 1, so it is plus 1. But when x is approaching negative of 1 from positive side of negative 1, that means limit it is negative infinity. So this is the RHL, right hand limit, and this is the LHL. So LHL is finite, but RHL is negative infinity. So essential discontinuity at x equal to negative of 1. So either of LHL or RHL, if any of these limits is plus infinity or minus infinity, the function has a break or discontinuity, and that discontinuity is a essential discontinuity type. Okay. And this is another plot. See, this is the function, this is x equal to 2 point, this is x equal to, sorry, this is, consider the point x equal to 2, this is x equal to 2, this point. So when this is fx and this is x, as x approaches 2 from positive side, x is approaching 2 from positive side, this is x axis and x is approaching 2 from positive side, the value of the function increases to positive infinity. So limit x tends to 2 positive fx is positive infinity. Whereas as x approaches plus 2 from negative side of 2, the value of the function is approaching negative infinity. So limit x tends to 2 from negative side fx is negative infinity. So again the function has an essential discontinuity at x equal to 2. Here LHL is negative infinity, this is LHL, and RHL is positive infinity. Okay, so this is essential discontinuity. Okay. So if you recall the plot of tan function, if you recall, this is tan x and this is x is in radian. So tan function looks like this. So this is 0, this is pi by 2, this is pi. So this is again negative pi by 2. So as x approaches pi by 2, tan x function limit x tends to pi by 2 from negative side, tan x function approaches plus infinity. This is plus infinity. Whereas tan x function, when limit x tends to pi by 2 from negative side, tan x, if we evaluate, then it approaches negative infinity. So right hand limit is for tan x function negative infinity, right hand limit is positive infinity, right hand limit when you are approaching pi by 2 from negative side of pi by 2, it is plus infinity, whereas left hand, this is right hand limit, this is actually, this is when x is approaching pi by 2 from negative side, so it is left hand limit, it is positive infinity. Whereas when x is approaching pi by 2 from negative side, from positive side, this is right hand limit, it is negative infinity. Okay, so left hand limit means when x is approaching from this side, left hand side, its value is plus infinity. Whereas when x is approaching pi by 2 from higher side, positive side, that is right hand limit, it is negative. Okay, so it is just reverse of the previous one. So tan x has a essential discontinuity at x equal to pi by 2, and many other such points are there on the tan x curve, but these are all essential discontinuities. Okay. Now another type of discontinuity is removable discontinuity. Removable discontinuity is what? If the function, a removable discontinuity occurs when the otherwise continuous curve has a hole at some point. So if limit x tends to a plus fx and limit x tends to a minus fx, both exist and are equal, if it happens like this, both the limits exist and equal, but fa happens to be different or does not exist. fa either does not exist or exists, but fa is not equal to limit x tends to a fx. Then we have a removable discontinuity at x equal to a. That means this is a function, say for example, this is a function, it is like this, y equal to x plus 3, y equal to x plus 3 multiplied by x square plus 2x divided by x plus 3. So from this you can always write y equal to x square plus 2x, provided x is not equal to negative of 3, because at x equal to negative of 3 function is undefined. Okay, so for other x other than negative of 3, y is always x square plus 2y, y is equal to x square plus 2x, which is a parabola like this. Okay, and at x equal to negative 3 the function is undefined. Okay, okay, so this is x equal to negative of 3. The plot of the function is like this, it's a parabola. When x is approaching negative 3 from negative side of negative 3, that means we are considering left hand limit, it is the value of the function approaches this value, which is actually what? F of 3, f of negative 3, f of negative 3, for where f of negative 3, where f is actually, if had f been defined like x square plus 2x instead of this. Okay, let us consider this fx, why is this thing, this is fx, and let us consider this function gx is x square plus 2x. So from the plot you see fx is equal to gx for all x not equal to negative of 3. We can write like this, fx is equal to gx for all x not equal to negative of 3. Okay, and gx is this much and fx is what? If you remove this thing also, fx is actually x plus 3 into x square plus 2x by x plus 3. This is fx. And gx is what? Gx is x square plus 2x. Okay. Okay. If we write like this, so we can always write fx is equal to gx for all x not equal to negative of 3. And at x equal to negative of 3, fx at at x equal to negative of 3, fx is indeterminate. Does not exist. We can say fx does not exist. Now what we find, limit x tends to a, let us remove this thing. if we evaluate the value of the function, value of the limit x tends to negative of 3 fx, it is actually value of gx function at x equal to negative of 3, g negative of 3. Fx is undefined at x equal to, fx does not exist at negative of 3, but g, which is a reduced version of fx, it exists at x equal to negative of 3. So had there been no such hole, the function would have continued like this, and its representation would be like this: gx equal to x square plus 2x. So limit x tends to 3, negative 3 from negative side will be g of minus 3, and it is also equal to limit x tends to 3, negative of 3 from positive side fx. So both the limits exist, because when x is approaching negative 3 from this side, the limiting value becomes equal to this, and when x is approaching from this side, then also the limiting value becomes equal to this height. Okay, but unfortunately the f negative 3 does not exist. Because f negative 3 we have to calculate using this expression, because gx, fx and gx are equal for all x other than negative 3. So this formula gx cannot be equated to fx at x equal to negative 3. So at x equal to negative 3 you have to use this expression fx equal to x plus 3 into x square plus 2x divided by x plus 3. And if you plug in this x equal to negative 3, this yields a 0 by 0 result, which is indeterminate. Therefore f negative 3 does not exist. That means the function is discontinuous at x equal to negative of 3, because limit x tends to 3 fx is not equal to f of negative 3. X tends to negative 3 is not equal to f of negative 3. Limit x tends to negative 3, fx is not equal to f of negative 3, and f of negative 3 actually does not exist. So the function is discontinuous at x equal to negative 3. But see, if we had changed the definition of the function like this, fx is, if we define the function in this manner, that if we define the function fx equal to x minus 3 into x squared plus 2x for x minus 3, and if we write fx equal to x squared plus 2x for x equal to negative 3, that means if we define the function like this, for fx equal to x minus 3 x square plus 2x by x minus 3 for x not equal to negative 3, and fx is x square plus 2x for x equal to negative 3. Earlier the function is defined for as y equal to x plus 3 x square plus 2x by x plus 3 for all x. But here we are redefining the function. Fx is x minus 3 into x square plus 2x by x plus 3 for all x not equal to minus 3, and fx is x square plus 2x for x negative 3, x equal to negative 3. Actually at x equal to negative 3, value of this function is actually 9 minus 6 is 3. So if we say that f negative of 3 is 3, then if we define the function like this, fx is x minus 3 x square plus 2x by x minus 3 for all x other than negative 3, and f negative 3 is 3, then the function becomes continuous. That means this discontinuity or this hole in the function can be removed by redefining the function appropriately. Then we say this type of discontinuity is called removable discontinuity. Because of the very definition of the function, there exists a hole in the function, and by suitably redefining the function, we can remove the discontinuity. Okay, so what is happening? In this case, in removable discontinuity, both left hand limit and right hand limit of the function exist. They are equal. That means limit of the function as x approaches a, it is existing and its value is defined, but value of the function is not defined at that point, and therefore the function is not continuous at x equal to a. But if we suitably redefine the function, and if redefine the function, and if we give a finite value to the function at x equal to a such that the value of the function matches with the limiting value of the function, then the discontinuity can be removed. Okay, so this is a removable discontinuity type thing. I think what I wanted to convey is clear to you. Okay, so what you have learned, there are three different types of discontinuities. One is jump discontinuity, one is essential discontinuity, another is removable discontinuity. Okay, so with this I conclude continuity chapter continuity as per BC syllabus. So you have to solve good number of problems to have a command on this subject, and we will provide you a set of collected problems on continuity. So with this I conclude this topic on continuity for BC test, APBC test. Thank you.